In condensed matter physics and physical chemistry, the terms viscous liquid, supercooled liquid, and glass-forming liquid are often used interchangeably to designate liquids that are at the same time highly viscous. See viscosity of amorphous materials, can be or are supercooled, and able to form a glass. The mechanical properties of glass-forming liquids depend primarily on the viscosity. Therefore, the following working points are defined in terms of viscosity. The temperature is indicated for industrial soda-lime glass. In a widespread classification, due to chemist Austin Angel, a glass-forming liquid is called strong if its viscosity approximately obeys an Arrhenius law. Log eta is linear in 1/t. In the opposite case of clearly non-Arrhenius behavior, the liquid is called fragile. This classification has no direct relation with the common usage of the word fragility to mean brittleness. Viscous flow in amorphous materials is characterized by deviations from the Arrhenius type behavior. The activation energy of viscosity Q changes from a high value QH at low temperatures, in the glassy state, to a low value QL at high temperatures, in the liquid state. Amorphous materials are classified accordingly to the deviation from Arrhenius type behavior of their viscosities as either strong when QH QL QL or fragile when QH QL greater than or equal to QL. The fragility of amorphous materials is numerically characterized by the Dö-Remus fragility ratio RD equals QH/QL. Strong melts are those with RD1, 1, whereas fragile melts are those with RD1, greater than or equal to 1. Fragility is related to materials' bond-breaking processes caused by thermal fluctuations. Bond breaking modifies the properties of an amorphous material so that the higher the concentration of broken bonds termed configurons, the lower the viscosity. Materials with a higher enthalpy of configuron formation compared with their enthalpy of motion have a higher Dö-Remus fragility ratio. Conversely, melts with a relatively lower enthalpy of configuron formation have a lower fragility. More recently, the fragility has been quantitatively related to the details of the interatomic or intermolecular potential, and it has been shown that steeper interatomic potentials lead to more fragile liquids. The microscopic dynamics at low to moderate viscosities is addressed by a mode coupling theory, developed by Wolfgang Gatze and collaborators since the 1980s. This theory describes a slowing down of structural relaxation on cooling towards a critical temperature Tc, typically located 20% above Tg. Gatze W. 2009 Complex Dynamics of Glass-Forming Liquids. A mode coupling theory. Oxford University Press. Zarzaki J. 1982 Les Vers et la Tavatro. Paris, Masson. Also available in English translations. References